Hi, my name is Chrisomalis. My talk today is size ordering as a cognitive principle for numerical systems. Have a look at these two numerical expressions. Take a moment, ask yourself which number is larger. Probably you're able very rapidly to determine that the left one is larger. That's because in place value systems that have one sign per place, like the decimal, Indo-Arabic, or Western numerals, the expression that has more signs will inevitably be greater. Now, ask yourself for this next expression, which number is larger? These two Roman numerals are more difficult to compare. One of the reasons for that is that not all numerical notations have this property. So the Roman numerals, the conciseness of a Roman numeral expression is a poor predictor of its numerical magnitude. This is the subject that we're going to investigate today. Over the last 5,500 years, there have been over 100 structured, principally non-linguistic representations for numbers, used across almost every inhabited continent, used with a variety of literate and non-literate traditions. Numerical notations are partially integrated with, but separate from, writing and literacy. And of course, they're used alongside number word systems of individual languages, but they are translinguistic. That is, they don't have a single reading in any particular language, but can be read in many different languages as the reader prefers. To date, there's been ample research experimentally on numerical notations, but mostly that has been using place value decimal, that is to say Indo-Arabic or Western notations. And these are the most common systems used by almost all literate people worldwide. And so the last 30 years or more of this research has largely focused on reading and transcoding and errors and speed of reading Indo-Arabic numerals. But most of the systems ever used historically are now obsolete or obsolescent. And thus there's minimal research on the cognitive properties of the vast majority of numerical notations. There is a little bit of work on Chinese and Roman numerals, but far, far less. Inevitably, this sort of research presents a methodological challenge, which is unfamiliarity makes comparing notations in an experimental task challenging. In other words, participants are simply not as familiar with all the notations that they're being asked to work with. And that makes experimental research more difficult than it would be otherwise. Now, let's take a moment and look at the structure of numerical notations worldwide. All numerical notations fall into one of 5 basic types. And over the past 20 years, I've spent some time outlining a 5-part typology, which we'll be using today a little bit. Now, the Indian, Arabic, and Western notations that are used almost by everyone today are what I call ciphered positional. That is, they use one sign per power of the base, 10, and multiplication is implied using place value. But note that there are actually 2 different dimensions at play here. We can look at the additive positional dimension, and that corresponds to whether a system has place value or not. But we can also look at cumulative, ciphered, and multiplicative notation, and that indicates within each power of the base whether there's one sign, whether there's 2 signs, or whether there's multiple signs. And so we could sort of think of the notation within each power as a sort of intra-exponential, and across the different powers, the presence or absence of place value as inter-exponential representation. This is a very general account of what is a much, much more complex subject that I've dealt with in other papers. The central problem that I want to talk about today focuses first on the fact that understanding human numerical cognition requires that we study it comparatively across cultures and across time. Most number users historically were not familiar with the ciphered positional decimal numerals like those studied in many experiments. So today what I want to ask are, what are the properties of the full range of known numerical notations that might be relevant to understanding human numerical cognition? This is a weird problem because the populations we study are generally Western educated, industrialized, rich, and democratic, but it's also a modern problem. The sorts of people who use different notations largely don't exist today to be sampled, to be worked with. They're not available for our research study. And so we need to use historical data, and we need to examine the structures of systems. One way to do so is by looking at the conciseness of different systems. And I'll define conciseness of an expression simply as the length of, an expression, the number of graphemes or morphemes it has, whether that's 998 cm xcvii or 998. Those have different amounts of signs or morphemes for each expression. We can also study the systemic conciseness of a whole system. In other words, for a set of numbers from 1 to x, we can ask what's the mean conciseness of all of its numerical expressions. I'm going to now introduce a new concept, which is the concept of size ordering. And this has been a subject that I've addressed in my most recent work and that I want to spend most of the rest of our time on today. Size ordering is the degree to which the conciseness of a series of numerical representations is well ordered. In other words, the degree to which numerical quantity corresponds to the number of graphemes. We do this by comparing the conciseness of consecutive numbers. And we ask a question like, is the conciseness of n plus 1 less than the conciseness of its predecessor n? If so, that's a little bit unexpected, and that's the topic of our investigation. Now, I want to suggest that size ordering might be important and that there are good cognitive reasons to think so. One reason is that it's potentially related to the approximate number system, subject which has been investigated by cognitive psychologists for the past 25 years. The ANS allows us to rapidly compare the numerical magnitude of two groups of like objects, for instance, dot patterns, but that have unlike size, with unlike magnitudes that are more unlike are generally easier and more rapid to compare. Size ordering has a family resemblance to the ANS. Size ordering allows us to rapidly compare two numerical representations based on their conciseness, in other words, their unlike size, just as we did in the little tasks I gave you at the beginning of my talk. So how do we do this? One way to look at size ordering is through what I call representational smoothness. So for some set of numbers in some notation, we could take the mean of the absolute differences in lengths between all pairs of numbers n and n plus 1. So we see with the Western numerals at the left, there is no increase in size until you get to 10, and then it goes up by 1, from 1 digit to 2. But the Roman numerals go up, and then they go down, and then they go up, and then from 8 to 9, they go down by 2, and then they go down again. And so we can see that their representational smoothness differs, 1/9 versus 10/9. We could also investigate size ordering a different way through inversion by simply asking for some set of numbers what proportion of them have the conciseness of the number n greater than the conciseness of n plus 1. So for instance, the Roman numeral 24 is longer than 25. Or here for the numbers 1 through 10, we see that the Roman numerals 4, 5, 9, and 10 are shorter than the number that precedes them. So we could establish an inversion value of 4/10 or 0.4. So in the study that I'm going to present today, I investigated 11 numerical notations, selected across a comparative range of known historical systems over the past 5,000 years, across different structures, across different continents, across different time periods. However, all of them, except for obreo-kaimi, which is a 20th century West African invention, were used for 1,000 or more years. For each, I investigated first the conciseness of each expression from 1 to 1,000, evaluated across each system, and then took the mean systemic conciseness for that system. And I then looked at size ordering. And so in other words, looking at each pair of consecutive numbers, asking, does it increase or decrease in conciseness? And does it invert for the numbers, again, 1 to 1,000? So here are the systems I looked at, and I've just given a sample expression of 228 for each one, along with the base and, if relevant, the subbase of the system. I don't have time to go into all of these, but note that there's an enormous difference in the conciseness of these. 228 in obreo-kaimi is just 2 signs, and in the Aztec system it's 19 signs. But also note that there are all sorts of different complexities that are represented by these representational structures. Some of them are multiplicative or have multiplicative elements. Some of them are straightforwardly cumulative additive. Some of them have other sorts of things going on. I don't have time to talk about all of these today, but it's worth noting that this is what creates these differences in that we're about to see and we're about to discuss. So let's look at the conciseness, smoothness, and inversion of all of these systems. So immediately we can see that the Indo-Arabic system does pretty well on these accounts. It is fairly concise, but it is not the most concise system. Both a ciphered additive system like the Greek alphabetic system and a ciphered positional system like Obreo-Khaimi with a base of 20 rather than 10 are more concise than Indo-Arabic ones. In fact, positional systems are not more concise than additive ones overall. What actually makes the difference is the distinction between cumulative and ciphered systems. That systems that just use one sign per power of the base are the most concise ones, and systems that use many signs per power of the base are less concise. That's actually fairly predictable. But we can also see that there is an association between conciseness and smoothness. That systems that are not very concise also tend to not be well size ordered. And that multiplicative additive systems like Chinese are kind of in the middle, in between the cumulative and ciphered systems. Now, all of these systems, note, other than Obreo-Khaimi, which by all of these accounts is actually the best system, all of these systems were used widely for 1,000 or more years. So it's not the case that these are inferior representational strategies that were abandoned or that should have been abandoned. But it's worth noting that they have existed for a very, very long period of time. Now, let's move on and very briefly talk about diacronic changes, because we can also investigate what happens when systems change over time. Do they do so in ways that correspond with these properties? The Roman numerals changed over time. The early Roman numerals were purely additive. And the subtractive notation that we're familiar with was only introduced around the 1st century BCE, and it took actually a millennium for that to become the most common form. Now let's look at what additive and subtractive Roman numerals look like under this analysis. The additive Roman numerals go up in a fairly regular way. Each block of 5 has a step stair increase in conciseness and then goes back down at each multiple of 5. In contrast, the subtractive Roman numerals are somewhat more concise, but you can see that they're a little more variable, and that's because the multiples of 4 and 9 are actually lower than we might expect. In other words, subtractive Roman numerals are more concise than additive ones. However, twice as many subtractive numerals are inverted in length. In other words, they're shorter than their predecessor. But note that the inverted numerals don't drop as drastically. In other words, the difference between 9 and 10 is not as great. And so the subtractive system is a little bit smoother than its additive counterpart. In summary, despite claims to the contrary, Indo-Arabic notations are not more concise than all other systems. However, they are the most consistently size-ordered. Their conciseness strongly predicts their magnitude more than any other system. But because historical numerical notations are more structurally diverse than those used today, understanding how modern people read and transcode them is necessary, but not sufficient. Our assumptions about the efficiencies of decimal place value notations must be tested against what we know from other systems. Finally, some future directions. I think we can ask some great questions. For instance, to what degree are historical events of transformation and replacement predictable by some of these cognitive factors? I think we can also ask, to what degree does size ordering in numerical systems predict learnability among uninitiated users? In other words, experimental populations who don't know these notations until they're introduced. Finally, I think we can ask, to what degree does the ability to use size ordering or other properties of numerical notations correspond to the use of the approximate number system, bringing together historical and experimental findings into a synergistic correspondence. Thank you very much.